This is 9.12, angular momentum. Today we're going to calculate angular momentum and angular impulse. You're going to see that it's very similar to linear impulse and linear momentum. We're going to put an R in there. That's the only difference. All right, so yesterday we learned about linear stuff. Today we'll be talking about angular stuff. What's angular mean? Do you remember? Angular. In radians. Okay, we're getting close. It's in degrees, so it's a circle. We're going to talk about angular means circular, right? So this is momentum on a circle. If I spin my fancy little object here on this, I can give it some force to get it to go, and then once it starts going, I can stop giving it force, and you can see that it continues to go around in that circle for a little while until it has enough force or enough air friction to slow it down. All right, so it's that tendency for it to continue to go in a circle since it has momentum. So that's what we're talking about today. So here's your equations. For the most part, for an object on a circular path, you're going to use MVR. And this L, this capital L, is talking about angular momentum. Now, if it's not just an object on a circular path, like my little object here, my little washer, it's actually a magnet, it's on a string. This would be an object on a circular path. That's fine. But if I go and look at my meter stick and I spin it around the center, I can't use MVR anymore because it's not an object on a circular path. Instead, it is an object that has mass distributed evenly across it that is being swung and it's rotating. The object is rotating. So it's not being swung in a circle, instead it's rotating. That means that I need to use its specific moment of inertia, that's where the I comes in, times its angular velocity. So for this object, I can't use this because it's not an object on a circular path. Instead, I have to use this, and if I'm spinning it at its center, it's going to be 1/12 mr squared. If I was talking about like a disk, a solid disk, then I'd have to use 1/2 mr squared. So you'd have to use its specific one. But for the most part, objects being swung on a circular path, you can use mr squared. So mr squared. And then this is omega, which is V over R, I think. So if we look at this stuff, if you say it's an object on a circular path, which is mr squared, and you look at omega, which is like this, so omega is going to be V over R, and you go L equals I omega, and replace these things, mr squared with V over R, that's where the MVR comes from. So that is the same equation if you're looking at the moment of inertia for an object on a circular path. So for that specific object going in a circle, you can use either one of these. It will work just fine. It's just when you start talking about other objects with different mass distributions that you have to use this one instead. Can you move your cup to the corner so I can see it? Thank you. All right. So then, if we translate this stuff into angular, remember that the one that I gave you yesterday was this big long equation that kind of covers everything. It's the force times time is equal to impulse, which is J. I keep making a tau. I'm sorry. That looks terrible. Too much torque going on here. Tau. J. That's a J, right? Yeah. Okay. And this is the change in momentum, which is the basically V final minus V initial. So that's what I gave you yesterday. This is just translating all that linear stuff into angular. So force and torque. Torque is the angular of force. Time stays the same. It's going to be equal to our impulse, And this is going to be angular impulse, which is just a little different than normal linear impulse, is equal to the change in angular momentum. You guys with me so far? Which is going to be, you could go MR and then V final minus V initial. But it is better because a lot of the times when we talk about the object changing its radius, to look at it like this. That's a little bit wider range. Because now it's saying that your masses could vary from initial to final, your velocities could vary from initial to final, and your radius can vary. And a lot of times the mass won't change, so the mass here will be the same as the mass there. But that way it covers all your bases. You can also replace this with if you're given moment of inertia and omega instead, since they are equivalent.
So do those two radicals
It's just that this stuff is the linear stuff, and this is the angular stuff, and this is basically the same as this. This you just use when you're not talking about an object in a circular path like the Earth. Instead, you're talking about like mustard, right? Or you're talking about like a solid disk, which most of your stuff won't be. But you can use either one for an object on a circular. Okay. So, conservation of momentum. If you look at this equation, the only way you can change momentum is if you apply an outside force. If you do not apply an outside force, that means zero force, zero torque, that means there's going to be no change. If there's no change, that means that these two things have to equal each other. So the momentum initial has to equal the momentum final. And imagine, the best way to do this is to imagine an ice skater. An ice skater sitting on the ice. It's frictionless and she's spinning, right? If she's spinning, and she wants to go faster, right, she can't apply an extra force because she's on frictionless ice. So she can't like stick her leg out there and be like, I want to go faster and spin like this. That's not going to happen. So she can't apply an outside force, meaning that her momentum is going to remain constant. It can't change. But she needs to spin faster. So she can, we'll just say she keeps her mass constant for now. If she reduces her radius, so brings her arms in, she's going to spin faster. Does that make sense? I'm sure you've all seen that. No? Dead faces today. Okay, that's fine. Continue. All right, the other thing that she can do is, let's say that she's in as tight as she possibly can go. So the radius is small. It can't change. So she can vomit, right? Lose some mass. Now she's going to go faster. Okay. Yeah, it's a little gross, but it works. She's trying to go faster. Do you see how this kind of works? Okay, I have a big practice question for us today. This should hit every single piece of information that you need for the most part.
Is that the end of the notes?
That's the end of the notes. I'm going to do a practice and then we have further questions. All right. So a 2-kilogram ball is connected to a string with a length of 1.5 meters. It swings around in a circle. It makes one revolution every 0.25 seconds. What's the 2 kilograms?
Mass.
What's 1.5 meters? What's the one revolution? It's kind of a distance. We'll just leave it there for now. It's not that important. We'll get there. It's kind of theta, actually. 1 revolution theta. Yeah. Kind of. Okay, and then 0.25 seconds. What's that? Time. And this is time for 1 revolution, so it's actually technically period. So you can go like this if you want. Or you can think of it as T. It is technically period since it's for 1 revolution. Okay, we have kilograms, we have meters, we have revolutions, we have seconds. Which one of these is not in the proper SI unit? Revolution. So what should we change it into?
2 pi.
2 pi radians. There we go. 2 pi radians. Radians is the correct one for us. All right. Our first question says, what is the angular velocity of the ball? So what variable are we looking for when we say angular velocity? It's not V. Angular velocity, the one in the circle.
Omega.
Omega, there we go. Omega. And what's the equation for omega? Do you remember? I can remember the equation for normal velocity. No? Nobody? About distance over time, velocity. So if we're talking about angular velocity, what would it be? Angular distance over time. So it should be theta over t. All right, if we want to do this, theta, 2 pi radians over 0.25 seconds. What do you get? .12, and this is radians a second. Okay. B. What are we looking for? Tangential velocity. What variable is that? V. Good. V. All right. So we're given omega. How do we get omega into V? Remember? You might want to pull up your note card from chapter 8. Sounds like you guys are having some hard times with that.
Distance traveled over 1 revolution times 2 pi.
That was this one. But we're looking for how do I get this one into this one. So look for an equation that has omega and V in it.
V equals radius times omega.
Good. V equals R omega. So V is going to be R, 1.5, times 25.12. That's going to be, that's really high. Yeah, that works. Okay, 37.68, so 37.7 meters per second. Part C. What's the moment of inertia of the ball? What variable are we looking for? I. And it's a ball on a circular path, so what is its moment of inertia? What equation? mr squared. Yeah. Mr squared. So I is going to be 2 times 1.5 squared, which is going to be 4.5 kilograms meters squared. Okay, then we're going to do D. All right, we're actually getting into the stuff that we learned today. D, what is the angular momentum of the ball using velocity? So what variable are we looking for when we say angular momentum? Capital L. What equation are we going to use if we have to use a V in it? NVR. Good. NVR. So this will be L equals M times V, which we found right here, 37.7, times 1.5. and that gives me 113. All right, then I'm going to look at E. It says what's the angular momentum using I now? So what variable are we looking for? Capital L, still. And what equation are we going to use instead of the MPR? I omega. So L is going to be I, which we found to be 4.5, and omega, which we found to be 25.12. And that gives us 113. So as long as the ball is on a circular path, and it's not some sort of like weird object with weird masses distributed all over the place, it doesn't matter which one you use, you're going to get the same answers. You can use either one, depending on the variables you're given. Okay, we got one last one. This one's a little tricky. It says F, what's the final angular momentum? So we're looking for LF, but it gives us a force of 6 newtons that's applied clockwise, so clockwise would be negative, for 0.11 seconds. So time is going to be 0.11 seconds, and this should be a negative 6 because it's applied clockwise. So it's going to slow the object down a little bit, act in the opposite direction which it's going. All right, which equation do we want to use? Which parts of the equation do we want to use? Look up there.
Force times time.
Force times time would be really nice if we could use that, except that this is for linear stuff. So we're going to use the same thing but for angular. We're just going to use torque times time because our object is on a circle. If we don't use the angular stuff, we're not going to get the right answer. So how do we get torque? How do we get force into torque? Remember the equation? Fr sine theta. And remember, when it doesn't give you an angle, you can assume this is 90 degrees, so this thing will just go to 1, and you'll just have Fr. So we're going to use torque times time equals, which other part of the equation do we want to use? Delta L. You can use this stuff if you want, but it's going to, we already did all the work for it. So let's look at delta L, which is just L final minus L initial, where these are our L initials. This torque we already found to be Fr sine theta, and the sine theta goes away. So it's just FRT equals L final minus this 113. So we have negative 6 times 1.5 times 0.11 equals L final minus 113. And that gives us 112. So that's the only real tricky part there. Make sure that you're using the angular stuff since it's an object on a circle. Okay, I have 3 clicker questions for you. You guys ready? Well, I'll let you finish copying that down. I'll pass out the worksheet. Let's end this really fast.